Hey, hi, welcome to this session. Thanks for attending. I'm Venkat. I'm the product manager for Views GSI. And in this session, I'll probably try to give you an overview of what indexes are, and I'll try to answer why you should even care about it and what it brings to the table as such. And if all goes well, I will attempt at a live demo and show you the power of GSI. So, indexes as such, if you remember, in the good old days of library, when you used to go to a library, you had this entire card catalog division, right? As in, you used to go there by, this is a Library of Congress photo, but essentially, in the general world, you have catalogs split into multiple ways, right? And then the index catalog has either by author names, or by genre, or alphabetical titling and ordering of the titles. So you could go to either of these catalogs, and then from here, pick up the exact book that you want, and then go to the actual book and pick it up. Indexes do exactly the same. You have a huge data set, you want to efficiently access it. How do you do it? Indexes give you the direct record to the place where the data set resides. And that's exactly the idea carried forward from this. Essentially, you create multiple indexes based on the different types of query patterns that you have. So in the earlier session, when you saw about Nickel, the way you query, you essentially, what powers Nickel at the back is the GSI, the indexes. And the way you move from the card catalog to the book, to the actual record, to the actual book, that's exactly is what is being done in GSI. But there is a basic question, right? As in, okay, all that is good. What is the actual problem that is being solved? It fastens, it's steroids for queries. It makes queries really, really fast. And I'll be double-clicking many of these things. So when you make it fast, the query latency is reduced. And what happens if the query latency is reduced? Your users don't have to wait for results, right? If you don't have indexes and with and without an index, there's a huge difference in query latencies as such. And the next is, you spoke about throughput, latencies. Essentially, there is a cost, there is a cost associated to everything. In the engagement economy, as you see, if you make your customer wait, you're losing your business. You can't do that. And that's why GSI indexes are very important. So let's take a sample, right? So when you install Couchbase, you get something called as a travel sample. It has around 31,000 records, 31,500 records. And if I just do a select star from travel sample, just use a type and don't create any indexes, the amount of time it takes, and if I create just an index as such, right? On one of the type columns, what happens? You see close to more than 100x factor difference, right? We are talking about 3 seconds to less than 35 milliseconds. And this is just a result that I get by running Couchbase on my laptop. And this is a very small data set. But the idea is the same. So how do you know whether a query is using an index or not? So we have something called as an explain plan that gives you an idea of what is happening behind the query. And you will see that when there is no index as such, the Nickel query goes and does a complete primary scan. And that's why you had like 3 seconds of latency time. And with an index, you will see in the explain plan that there is the operator as such is index scan. So this is one quick cue for you to identify whether a query is using an index or not, right? So we looked at latencies, right? But indexes also solve a very important problem of the amount of data that is transferred between the index nodes and the data nodes. So this is something that we have released in 5.0, which essentially shows the data that moves and the data under the hood, what is happening with the scan. So if you see from left to right, in the primary scan, you're actually sending close to the entire data set back to the query nodes. So amount of data that is moved is almost the whole data set. But if you just have an index, whatever fits that index, in this case, we had type equal to airline, only 187 rows are being sent. This is the impact. So your network costs, your network data costs also reduce a lot. Same idea. Let's take one more example, right? In this case, I do a count. So in the last example, I just queried all the records. If I do a count of 1, just how many records are there in the database? Again, quite a lot of records being sent. But when I just have a simple index, just 1 row is being sent. So this gives you an idea of, I underscored two things here, right? One is latency, second is the data costs, right? Now let's look at, when you have indexes across, you have different types of query patterns. So each of your nickel queries does many different things. You have array index, array operators and whatnot, expressions you will be having. If you don't have any of the indexes, you just have a primary index, your nickel queries are going to do a full table scan. And as you saw, your latencies and your data costs are going to explode. And that is the reason why in Couchbase we have different types of indexes. I'll not go into detail of each and every one. So primary is what you index on the key as such. You can name it, so it becomes a named primary. Secondary is essentially, if you have a JSON document, the rest of the fields that you index are the secondary fields. Composite is a set of fields that so it's not just one field as such. You can have a set of fields that you'll be indexing. That's called as a composite. Functional is essentially if you want to index by an expression, let's say upper, lower, those becomes a functional. Array in JSON, you obviously have arrays. In Couchbase, we have a specialized index for arrays, which actually optimizes the amount of data that is transferred and also the query throughput as such. This is a big thing in array indexing because JSON has a hell of a lot of arrays as such. And part of it is actually used in what is called as adaptive index at the bottom. So you'd have heard of flexible indexing, adaptive indexing are similar, the same nomenclature as such. What adaptive indexing or flexible indexing does is you can actually not create specific indexing, but you can create a pair of whatever fields you have. It creates a big cluster of indexes, and the query actually optimizes and knows which index to pick as part of its query scan. Covered is, okay, we saw about the amount of data that is being sent from the index to the data array. Now, is it possible that I don't even go to the data nodes to pick the data and then send it? Can I just do a one hop? So the query actually goes to index nodes alone and gives me the data back. So covered indexes actually store the data in the index nodes as well. Otherwise, there is a hop that the index node the query goes to the data nodes, picks it up, and brings it back to the query nodes. Partial is, as of now, all our indexes stay in one. So if you create one index, it just stays in one node. But if you have a massive data set and your index cannot be residing on a single node, you can actually split it by a particular vector. That's what partial indexes are. We are working on optimizing this. So as a PM, one of the things for me is how do I make things simple, right? So I'll be talking a lot about it. So underscoring one of the earlier slides on covered, why did we create covered? So you saw different types of indexes. Why did Couchbase create these? Again, underscoring the same idea of impact of a covered index. If you don't have, queries still work. It's not that it's not going to work, but if you have a covered index, your queries are much faster. The hop to the data nodes are avoided completely. Now, that is the context for why we created and what is the impact of indexing as such. Now let's go a little deeper into the architecture of, at a very high level of how indexes work in Couchbase. So one of the primary and biggest differentiators for Couchbase is the idea of MDS, or multi-dimensional scaling. So in Couchbase, what happens is your data nodes, you can segregate your workloads. You have workload isolation. Your index nodes, your data nodes, your query nodes all work independently. There is a separate workload isolation here. And essentially, if you see, you can very much run all the services on a single node, but we have seen that most of our customers actually run specific workloads on specific type of hardwares. So for example, index services that run on hardware have very high RAM, whereas queries have very high CPUs. Data has a mix of these two. So MDS is extremely important for us for providing incremental innovations that we continue to do. For example, the way our genesis has happened, we started with KV, we had query, and then GSI came in. This MDS actually gives us the ability to keep on adding new features to our existing value prop. So how is that possible, right? So let's take a simple example. When I talk about MDS, what is the resultant of a decoupled architecture? Essentially, what happens is, let's say your writes happen to your data nodes. And each of these updates that happen to the data nodes, the indexes get updated asynchronously. Indexes don't have to wait for the data or have to block the writes to the data. So your effective throughput of your data nodes continue to remain as is. And this is asynchronously updated. So we saw some of the basic context of indexing, a little bit of how indexing works. What I'm trying to do is simplify things. Indexing as such is an extremely complex topic in terms of the way it heavy lifts data. Now, how do I simplify this? How can I make my users not worry too much about it and make things as simple as possible? So as you saw earlier, you just create an index. So you know what is the kind of queries that you're going to run. For any life to take place, you need a birth. And for the life to take place, genesis is just by creating index. And you can do it at any point of your time of your application. You create your applications, you keep on seeing the kind of query access patterns that happens. Then you go ahead and create or alter your index, just see how it works. Okay, so index has been created, queries have been served. Again, life cycle. The idea of impermanence is very important. What you have today, you don't have tomorrow, right? Philosophical aspect of it. But if you don't like an index, you want to create something else, just go ahead and drop an index. As simple as that. So the whole life cycle is just in 2. That's a simplified part of it. But with 5.0, we actually brought in a big paradigm change in GSI. What is that we did? Was 3 important vectors. And this is not a marketing pitch, by the way. We actually worked on, delivered, and whatever I'll be double-clicking each of these things in terms of what exactly we did. Performance, as you saw, performance is most critical for us. A Ferrari cannot be built after you built a Honda or a City. A Ferrari has to be built from day 1. Performance is critical for us from day 1. If we don't hit certain performance vectors, we don't release it. And we have done some amazing work here. Agility, we have seen indexing work. You can create indexes at any point of time. Manageability, okay, you have created all these indexes, but how do I manage it? How do I know whether they are being used or not? Or if I want to scale it out, how do I do it? If I see that there is a seasonality to my queries, if I want to add more index nodes, how do I add more index nodes to it? This is exactly what we'll be talking about. So far the indexing journey has been, GSI was launched in Couchbase in 4.0 a few years back. And then we had this idea of covered indexes, wherein I showed you what is the impact of covered index. And then in 4.5, we have something called as MOI, which is memory optimized indexes. So before when 4.0 was launched, we had something called as ForestDB. But ForestDB had its own problem in terms of not utilizing the memory architectures. And as you see in the last few years, the importance of memory, RAM is extremely important, right? As in the computational power is in a different league altogether. How do you actually provide our experience to our customers who can leverage this hardware? That's how MOI came in. And with 5.0, you saw the 3 vectors. That's exactly what I'll be talking about. We have launched a new storage engine in 5.0. This is a completely brand new storage engine written from scratch that we are launching in 5.0. Replicas, I'll be talking about index replicas, and something called as pushdowns. Pushdowns have existed since 4.5, but we have taken it to a different league in 5.0. So let's talk a little bit about Plasma. Many companies as such, they are actually acquiring companies for storage, to create the storage layer. In Couchbase, we have actually written this from line 0 inside. Okay? And we have actually, it's not that we look at the hardware capabilities, the changing hardware scenario in the world, the impact of SSDs, DRAMs. So how do you actually leverage our memory-first architectures and provide a kind of experience which actually leverages the hardware? And we also, many of the indexes as such use B trees and B plus trees. Here we use a lock-free data structures here as kind of modified higher order skipless. And we also take persistent snapshots. So if the node goes down and you bring it back again, the index is created from the snapshots as such, right? All these are completely abstracted away from you. Similarly, I'll talk about DGM. So let me double-click DGM. DGM is extremely important. See, many of our customers say that in MOI, our entire index has to be in memory. But with humongous data loads, you can't essentially have everything in memory, right? You need to have only a subset of data. So in Plasma, in the current, what is available with 5.0 today, we can go up to 20% DGM. And we are going to push the boundaries in the subsequent releases with that. DGM is extremely important. So these are some of the features of it. But what is the benefit out of it, right? Lower latencies, your throughput increases, your memory and disk usage, what was occupying quite a lot of memory and disk as such, with Plasma, it has reduced substantially. The next point is extremely important for us, which not many companies do as such, which is lower write amplification. the way SSDs work, and many of the administrators might not know about this, is the way certain softwares actually work with your SSDs, it's actually killing your SSD. Because in SSDs, every time you write, it actually does a to write, and there's a garbage collection that happens. So due to, and it's kind of a longer term volatile memory. During the passage of time, actually your lifetime of SSDs actually drops. Can we actually give an experience to our customers that your TCO, because there's a cost associated to changing your SSDs as such, can we actually give you an experience that you don't worry about it, but we take care of this write amplification factor? And also when you create the indexes, can we do it faster, right? So double clicking on the performance compared to what was there in ForestDB, this was the standard GSI that we had till 5.0. It's 3x, latencies are 3x lower. Throughput is almost as, this is not percentage by the way, this is 8x, magnitude of 8x better, okay? And so in indexing, as you saw, this is asynchronous, right? So essentially we have this idea of tunable consistency models. You can either wait for all the writes to propagate to indexing and then query, or if your thing is not so critical, if your queries are not so critical. So we have this idea of not bounded. When you say not bounded, whatever is present in the query, just give me that. The numbers that you see in 3x and 8x is actually what read your writes. See the number 50x and 120x. That's what happens if you don't wait for the complete consistency as such. Let's look at one more. Compare. We looked at latency and throughput. In terms of memory, again, with ForestDB, substantially lower memory consumption. One good thing is that if you're already using, how many of you are already using ForestDB or any form of GSI in your existing clusters? We are doing an automatic upgrade of all your ForestDB to Plasma. If you're an EE customer, you don't have to worry about it. It's a seamless experience. Things work. Should work. Okay. So a summary of different things. So essentially, this is an important slide in terms of the overall scheme of things of different storage options. And one thing that I forgot to mention was Plasma is the default standard GSI with 5.0. Okay. So for our EE customers, okay, let's go from left to right, right? Performance. The reason why MOIs is in green is, since everything is in memory, you get really fast speeds. But Plasma is in orange because it is almost as good as MOI in certain cases. When the mutation rates are very high, only then, but if you see the subsequent column, DGM, MOI goes into a pause mode when you run out of memory, whereas Plasma continues to operate as is, which is a very big value prop. And we have seen almost 85 to 90% similar performance with Plasma compared to MOI in most of the customer workloads. In fact, it's more than 90% in some cases. We have introduced this idea of replicas. I'll be talking about it in the subsequent slides. And both Plasma and MOI are available only for our EE customers. Because we have invested quite a lot of resources on this, as you see, some of the performance benefits that you get is in a different league altogether. And we want to make sure that our EE customers benefit from it. Okay, so we saw the performance aspects of it. We are in Silicon Valley. I need to have a picture of a cat if I'm going to talk in a technical conference. So if you just have one index on a single node, and if the node crashes, you have a problem. So for better query throughput, or even for HA, you need to have multiple replicas, right? So that's why in 5.0 we have launched something called as index replicas. The cats speak for themselves with their nice colored eyes. Earlier in 4.5, before 5.0, essentially what you used to do was you had to create the same index with a different name. It's the exact same definition. Each of these things, you have to go to each node, run it, and it worked. The query was kind of smart enough to know which index to pick up. Things worked. These were called as equivalent indexes, but there were some limitations, right? You had to manually go and create. There was no placement rules. And if you are using index hence, in terms of use index, so if you see in the earlier slide, if you had used IDX1 alone, every time you had to go and change your application, as a developer, I'm not sure why you have to do that. You have to just, as I said, just 2 commands. If you're using use index, just think about one index name alone. And your prepared statements won't work, and rebalance will not work in equivalent indexes. All these problems are solved. So if you already have equivalent indexes in your cluster, let's say you have the similar kind of configuration, and you want to move to a homogeneous set, right, on 3 different nodes with the same index name. Earlier, you were running 3 different commands, just now 1. You either do num replica is 2. So what num replica 2 does is 1 plus 2. So you create 1 copy and 2 more. Sorry, 1 and 2 more. So there are 3 copies as such. If you want specific index placements, you can just give the IP addresses and be done with it. Simple. Can I take the questions later? Yeah. Yeah, index replicas. Advantages, as you know, as you saw, num replicas. So we have our own rules, which actually goes in places when you don't want to worry about the IP addresses and whatnot. Just create num replica. It goes and finds out, has the intelligence to find out which server groups that you want to put in. And even when one of the node goes down, the index replicas continue to run as is, because you have a copy of an index. You are load balancing queries, as was the case in equivalent indexes. Swap rebalance. So let's say you have 2 index nodes, right? One of the node goes down. When the node comes back, in equivalent indexes, you have to go and recreate the index. In this case, when the node comes back, we automatically create it. You as an administrator, you just have to take care of rebalance, nothing else. Easier manageability. And because of all these things, if you see, just by having 2 commands, your TCO, just imagine your TCO. TCO is just not about RAM and other things, right? There's a huge other, human factor to it, a humane factor to it. So how do you make it much more simpler? Your TCO cost, I don't have a number model to it, but we have seen that the return on investments with this kind of a model is much more substantially higher. So number 3 was push down. So when we talk about this query access patterns, if you remember in one of my earlier slides, the amount of data that gets moved from index nodes to the query nodes, that's very critical. What pushdowns does at a very high level is actually takes some of the predicates are the where clauses in your query, and puts it into the query to the index nodes, so that the amount of data that is retrieved is much lesser. And also indexing is it's Batman. Come on, it's going to do the heavy lifting. So that's what it does. It does all the heavy lifting and sends really limited set of rows in a really efficient way. So let's take an example. In the first case, let's say the select clause was the one. We had a limit clause, right? If you just go and create an index, still 4.5, we are not pushing down the limit clause. In this case, we are now. And similarly, in 5.0, we are also pushing offset. So if you are doing paginated queries, this is a very good use case of. And the resultant impact of it in terms of performance, again, the numbers speak for themselves. The throughput, the number of queries operated per second, these are not percentage, these are X. So we have increased in certain cases by more than 100 factor, right? Performance story. Similarly, one more case of the way we do certain pushdowns in the case of count distinct, if you see in the last row, and so composite filters. So I think the bar speaks for itself, right? The kind of performance difference that you get is huge. So just to double click some of this, index projection, count distinct is the last row that you see, select count distinct. In this case, we are actually, the index, the GSI client knows what needs to be pushed down. Having said all that, I wanted to show you a live demo. I think this is the fun part of it. And I'm going to try it, let's see. This is the environment that I'm looking at. I have a data payload, key size of around 23 bytes. I have a document of around 113 bytes. My node size is 24 physical cores, 64 GB RAM, and 512 GB disk space. I think this is a standard, it's not a very high-end system, reasonable hardware. I have an 8-node cluster, 6 nodes running data and query, both data and query, 2 nodes running index. I have one index, one primary index, which has one copy. So essentially, I have 2 copies of the index. And I'm going to be, for this, the workload that I'll be running is a YCSB-E, which is essentially 95% reads and 5% writes. This is, think of it like short-range queries that you will see in. So for example, if you have a discussion forum, if you want to get all the threaded replies for a particular thread ID, what do you do? So a sample query is written at the bottom. So for a given thread ID, if you want to limit by, let's say, 50 rows, what is that you want to do? And do you have any idea of what would be the kind of data set that you want me to operate on? Any sample data set sizes? Number of documents? Any suggestions? Few million? Few million is good? OK, I'll try a billion. I'm Batman. OK, so this is the tricky part, right? In the morning, we had some issues with the, during some of the things, but okay. So as I said, we have exact 8 nodes. I have 6 nodes of data and query, 2 index nodes, right? In this case, I already have just one bucket. As you see, I have 1 billion documents. And if you remember, I'm doing 5 writes. It's 5 inserts, 5% inserts. So already it has grown by 6 million documents. So I started this loads like a few hours back. Our performance engineer, Pavel, actually helped me to set this up. And I have an index which has a replica, very simple. So what is happening in the background is the reason why you see the numbers go up is the 5% writes. We have close to 500 Java SDKs, 500 Java SDK connections from the clients making to the server. They are inserting documents, updating it. So that's why the number, see, it went to 7 million now. And a sample, I can show you a sample document as well. It's a very simple document. It's kind of obfuscated. But the idea is, keep YCSB workload as such. And a few things that we want to see before we go to the actual numbers. So if you see the CPU utilization, we have 2 index nodes. The indexer consumes the lowest here. This is the kind of efficiency that we are talking about here, 30%, right? Overall, the RAM utilization is clean. Okay, the disk used across the data nodes is almost around 50 GB. Now, let me just double click on some of the operations. So what is happening now at the back? Ops per second. Before going to ops per second, let's go look at nickel queries per second. So take some time, but in this bottom, this, if you see, we are doing from the 500 SDK connectors, 500 nickel clients, we are reaching close to 60K nickel queries per second from the query nodes. This is purely from the nickel. We are starting with, because those are the nickel queries that are being fired. But what it goes to the next is, essentially, if you see this set, which is 2.85 million index scans. This is the index scan that is happening across both the index nodes. The data has still not gone to the data, so we are just talking about index scans. We are not going to the data nodes yet. So we are going from the top down. We have seen the nickel ops. Now we are seeing the index scan rates. And this one is the data. It's essentially the KV, right? 2.7 million average ops per second. It's almost as good as your index scans. So if you see here, this is exactly, the sets are the writes, right, 2009-31. Any other important? Okay, let me go to the fun stuff here. So those are the high-level numbers that you saw, right, in terms of requests and other things. So let me go and kill one of the index nodes and see what happens. Is that fine? Yeah. Okay. I'm failing over a server, as in one of the index nodes. I go back to statistics. I look at all nodes. I look at nickel query throughput. A really small drop, but smooth as a butter. No impact to your applications. Your application continue to run as is. Let's look at KV. Again, no impact. And okay, this is the application performance. Let's look at the system. So this node has gone down, right? So if you see the CPU is less than 1%, it's not taking traffic. Because it has taken in, this index node has taken in all the traffic now. That's why the CPU utilization kind of doubles. But if you go back to the servers and statistics once more, let's look at the index. So you see here, there's just one index stats, right? So now this replica, the spike that you see from 1.5 to 2.7 is exactly what happens when one of the replica fails. Things continue as is, systems continue to run as is, your applications continue to run as is. Was it okay? Just create and drop, that's it. Now, I'm not going to rebalance this because, what happens if I want to bring this back is to go, do a rebalance, recover, etc. It's going to take some time because we are talking about a huge, I've not indexed a subset of the documents. I've indexed 1 billion documents here. In this case, close to 1.7 billion documents. So it'll take a long time, at least an hour or so. We can optimize that as well, but this gives you an idea of what happens underneath the layers of indexing service. Oops. So I had this as a backup slide just in case my live demo does not work. I'm glad. Right. So we looked at the performance aspects. I tried to give you an idea of how things are as simple as possible for you from both an administrator perspective and also from a developer perspective. A little bit more double clicking on the other operations aspect of the indexing, right? So since we have replicas now, all the scale up in the sense, if you have smaller index nodes, let's say in this case we started off with 64 GB RAM, you want to move to a 128 gig or 256 gig, it's very easy for you to move. Those replicas give you that aspect because it automatically goes and creates the replica. So you just swap rebalance the nodes, and things work as is. Similarly, if you want to scale in, because of a seasonality, you move to a bigger node, now you want to go back to a smaller node, things work as is. Again, scale out and scale down, if you want to add and remove capacity, all the index operations are very seamless. The only thing is that create replicas. Without replicas, none of this will work, right? So that's why I would call, the analogy is GSI is the Batman of the data world. I think there is quite a lot of complexity as such at the back that is completely abstracted away, and that's what you need from the Batman, right? Gordon is nickel, Batman does all the work, gives it over to nickel, and that's about it. And that's how we tango, nickel and GSI, we tango together like that. Again, we operate in the dark. Not many know about it, but as you saw in the ops, we do the heavy lifting. There is a location aware. Index knows where exactly the data resides. We go and take the data like Batman. Things are simple. We are both agile, and also we bring in agility to the system. And we keep the city clean. You will know soon. There's more to it. So with that, I'm kind of done. I'm more than happy to take any questions. Sure. System performance? No, so since you have a replica, in our case, so the question was, what happens to your query performance during rebalance? As you saw in this case, even when I remove a replica, system continues to run. In this case, if I bring back the node, the load on one of the systems, which was close to 60%, will again come back to 30%. Things continue to run as is. Yeah.
Hi. I know that when it comes to rebalancing the data nodes, they have something not named delta recovery or something like that. That would actually just copies the amount of data that is missing. What about for indexes?
Okay, very good question. In this case, we look at delta recovery is possible, but in this case, when the rebalance happens, we try to recreate. It depends upon the time period of. Essentially, we would suggest. So when you do a swap rebalance, the system knows it goes and creates the indexes, which is missing. For in this case, when the other data index node is brought back, it automatically goes and creates the indexes.
From scratch, right from the beginning, or
it knows from where it has lost, and it goes and so all these things, the dotted line that you remember earlier, what consumes from data is DCP. Index actually works on DCP, so it knows where it was lost and it recreates from there. It does not try to do it from scratch.
Okay. So you're saying that if you enable the second index that you failed over, it should be pretty fast functional, right? You stopped it, and then
yeah. So there is some amount of recovery. There is some time involved, but there will be some overhead because the thing is, this is an eventually consistent model. So the index as such needs to keep track of what all changes have been done in the past. So there's some amount of overhead, but it's seamless. As a developer, you don't have to worry about it.
I see. Okay, thank you.
Ilsa? Yeah, sure.
You mentioned the asynchronous nature of the index update. And if you use fast queries, you it'll be fast, but it might not be correct. Do you have a guaranteed upper bound time that it takes to have that background job fire and update your indexes?
Oh, so the DCP, the updation is actually pretty fast. It's reasonably fast. Unless and otherwise a particular document undergoes huge mutation rates. Only then the system is not provisioned properly. Only then you have an issue. In most of our cases, we have seen it get it updated really fast. So one of the things that I can tell you if your index is lagging or not is if you look at the statistics here, there's something called as items remaining here. Sorry. Which will give you an idea of the amount of mutations by which the index. So if you see this total items remaining, sorry. Yeah. So if you see this total items remaining, this is the number of mutations that needs to be propagated to the index nodes. And in this case, if you see, it's just, even with a billion odd documents, it's just in the order of 100. So this gives you a good idea. So there are 3 consistency models. Actually, our docs talk about it. We have unbounded, request plus, and at plus. For the purpose of this discussion, I would highly recommend that you look at our docs. But that gives you an idea of, as I said, unbounded and request plus is given. At plus is if you know the timestamp of what is the consistency guarantees that the application decides. That also we give the option to the developers. Yep. No, there's no limitation as such. It's no. So since indexes, so the question was, is there an effect of performance on the number of indexes you create or the doc performance? The answer is no, because indexes are asynchronous in nature, and it's just that you need to provision capacity for your indexes. So if you, let's say you have only 5 data nodes and you have 100 index nodes, which I wouldn't understand a case by which you create that. But if you want 100 index nodes and you create 1 index in each of the nodes as such, it's possible. There's no effect of performance. In fact, your queries will be lightning fast because you have apportioned enough capacity in each of the index nodes. Yep.
One is data encrypted when it is at rest, the index data? And second is, what are the do's and don'ts of indexing? Like starts with works well when you are doing index rather than ends with. So are there any good do's and don'ts which we should take care of?
Sure. First question, data at rest. As of now, we don't encrypt at rest for now, but we have certain partners who actually, some customers use this, they have this enterprise grade solution, Warmetrics, I think, which they use for data encryption at rest. Second thing, in terms of do's and don'ts, it's a big topic in itself. Actually, we talked about it yesterday in the workshop. I can point you to the resources. At the highest level, it's all about the queries. I would say, look at your query access patterns. If your queries needs to be, first look at, what is, that you're actually fetching from your data nodes. If you know that, if your data model is fine enough, it all starts from a data model, to be honest. If your data model is wavy, things go for a toss. But even then, let's say if your nickel queries are doing certain access patterns, whatever is there in the where clause, if you take those and actually create the kind of indexes that you have seen, that actually is a very good starting point. Yep.
So I know that you talked about all of these indexes, and traditionally there's another thing in Couchbase, which is views. Is there any advantage of views over indexes?
Very good question. How many of you know views? Okay, so if you see here, GSI, let me give you a good primer of or everyone knows about the differences between GSI and views? Okay, let me give you a quick 1-minute TLDR. So essentially, views sit along with the data nodes. They are not an MDS-enabled service, right? They have a locality, so they are like local indexes. They sit along with the data nodes. GSI is completely MDS-enabled service, which is completely different, number 1. Number 2 is views are a scriptable way of doing things. You write your JavaScript MapReduce functions. So it's essentially pre-computed, pre-aggregated stuff. In GSI, we don't aggregate stuff for now. Important clause there. So that's a big difference. But we have seen that most of the customers who end up using views, they don't do any kind of reductions. They just emit a certain set of documents. which you can do it in indexes very easily. And views have certain rebalance operations issues, right? When your data nodes undergo a rebalance, your views are affected big time. So I would recommend that you look at GSI for if you're not doing any huge reductions. Let's say you have like a 7 billion document data set and you're doing reductions, pre-computed aggregates. Probably depending upon the use case, I would say views will work really wonders there. Some of those native reduction capabilities are not present in GSI for now. We are looking at it. If the use case is just to emit a certain set of fields from the document, go with GSI. So the question is, can I use in views? In views or GSI? For the purpose, let's take this offline. Okay. The question was, can I use multiple filtering and views? I would like to take this question offline. Essentially, it depends. John, you want to answer that? John, any comments on that? Or? Yeah, let's take this offline. It has its own things here. Okay, I think we are done. I'll be around if you have any questions, please.